Good morning all of you. Today I will discuss about the nuclear magnetic resonance spectroscopy. Nuclear magnetic resonance spectroscopy, in simple terms, it is said to be NMR spectroscopy. NMR spectroscopy is also called as the proton nuclear magnetic resonance spectroscopy. Name itself indicates it denotes the protons which are attached to the carbon. Definition of the NMR spectroscopy. Nuclear magnetic resonance spectroscopy, commonly referred as the NMR. In this technique, it gives the information about the physical chemical properties of the particular carbon compounds by dealing with the magnetic properties. Compared to the mass spectrometry, larger amount of the samples are needed but non-destructive. Next. Nuclear magnetic resonance spectroscopy introduction. Nuclear magnetic resonance spectroscopy is a powerful analytical technique used to characterize the organic molecules by identifying the carbon-hydrogen frameworks within the molecules. It gives the major importance to the drug discovery and drug designing techniques. The two common types of NMR spectroscopy are used to characterize the organic structure of the compounds, mainly proton NMR spectroscopy and C13 NMR spectroscopy. In proton NMR spectroscopy, it mainly deals with the carbon and attached to the indirect protons. And C13 NMR gives the direct information about the protons which are directly attached to the carbon. The source of energy in NMR spectroscopy is radio waves which have longer wavelengths and thus low energy and frequency. When low energy radio waves interact with the molecules, they can change nuclear spins of the some elements including proton and C13. Introduction about the NMR spectroscopy. When a charged particle such as proton spins on its and it rotates its own axis, it creates a magnetic field. That magnetic field is said to be induced magnetic field. Thus, the nucleus can be considered to be a tiny bar magnet. Normally, these tiny bar magnets are randomly oriented in this space. And however, this presence of magnetic field that is said to be applied magnetic field B0, they are oriented with the against of the applied field. More nuclei are oriented with the applied field because arrangement is lower energy. The energy difference between those two states are very small, less than 0.1 calories. This is the magnetic spin of that protons. They are randomly arranged in the field. When we apply the magnetic field, they are opposed. Some protons nuclei are opposed and some protons are aligned towards to the applied magnetic field. In a magnetic field, there are now two energy states of our protons. Lower energy state with the nucleus aligned in the same direction as B0 and the higher energy state which is nuclear aligned to the B0. When the external energy source that matches the energy difference between these two states applied, energy is observed causing a nucleus to flip from one orientation to another orientation. In this spin state, the energy absorbed by the spins and they are randomly flipped from one state to another state, from the lower energy state to the higher energy state. After the higher energy state, they lost the energy and converted to the lower energy state. This is said to be flipping. And equivalent and non-equivalent protons. Okay, equivalent means same, non-equivalent means unequal. Protons with different environments absorb different field strengths, while protons with the same environment absorbs at the same applied field strength. When the protons absorb the same energy of the field, that are said to be equivalent protons. There are energy different types of absorptions that is said to be non-equivalent protons. A set of protons are said to be equivalent if they have same environment and non-equivalent if they are the different environment. They are chemically different in the environment. Since each set of equivalent protons produces a different signals, therefore the number of signals in NMR spectrum tells us about the how many types of or how many sets of protons are present in the unknown organic compounds. Okay, this is the simple example for the equivalent protons and the non-equivalent protons. Here benzene, all the protons are arranged to the carbons. So these six types of protons these six protons are in the same chemical environment. Here also in cyclopentane, here also these protons, CH2 protons, are in the same chemical environment. These are the said to be equivalent protons. In simple acetone, these six types of protons are arranged in the same chemical environment. The CH3 protons are attached to the carbonyl group, and the CH3 protons are also attached to the carbonyl group. So these six types of protons are two sets of protons. Number of protons are 6, but they are arranged in the two sets, but both are in the same chemical environment. Both are attached to the carbonyl group. So these are the equivalent protons. And simple example or reference compound is the tetramethylsilane. In tetramethylsilane, 12 protons are in the same chemical environment, gives the singlet in the NMR spectroscopy. These are the non-equivalent protons. Here this methyl group and this methyl group is attached to the hydrogen, this methyl group attached to the hydrogen. These CH3 protons are the one environment, and these CH3 protons are in the one environment, and these four hydrogens are in the same chemical environment. So we get the only two sets of protons. Here also CH2 are in the same chemical environment. Here CH3 protons are in the same chemical environment, but these CH2 protons gives the one signal, and these CH3 protons are in the one signal. Chemical shift. The position of the signal along the axis of the NMR spectrum is called the chemical shift. The chemical shift of each signal gives the information about the structural environment of the particular protons that gives the signals. Counting the number of signals in a proton NMR spectrum indicates the first approximation the number of distinct proton environments in a molecule. Chemical shift may be defined as the chemical shift it is denoted by the delta is equal to shift in Hz by spectrophotometric frequency in Hz, in megahertz, in parts per millions. NMR scale ranges from the 0 to 13 ppm. Tetramethylsilane is the reference compound. It gives the signal at 0, and all the protons are in the same chemical environment. A signal that occurs further to the left of the spectrum than another, this is said to be downfield. A signal there right to the spectrum is said to be applied field. Upfield means that shows the compounds that shows the low magnetic fields or that shows the low chemical shifts. Downfield means deshielding. Due to the deshielding, that protons gives the high NMR values, high peaks, that moves to the right side, that moves to the left side. The protons moves to the left side, that shows the upfield or low chemical shifts. The protons moves towards to the right side, that shows the downfield or high chemical shifts or high NMR values. It is said to be downfield or upfield. Downfield means shows the high NMR values. Upfield means that shows the low NMR values. Next, the reference compound is that already I told that the reference compound is the tetramethylsilane. Here the protons, the methyl groups, 4 methyl groups contains the 12 protons. The 12 protons are attached to the silane groups. TMS is reference compound in the NMR spectroscopy. These 12 protons are in the same chemical environment, so they gives the only one peak at 0. The origin of spin-spin splitting. Spin-spin splitting arises because of the hydrogen on adjacent carbon atoms can sense one another. If the NMR signal is split by n equivalent protons, it is split into n plus 1 peaks. N is equal to number of neighboring protons. Here n is equal to number of neighboring protons. NMR spectroscopy mainly deals with the indirect information about the protons, that gives the indirect information of the protons that are neighboring protons, that gives the information about the neighboring protons. Equivalent protons do not split each other. Protons bonded to the same carbon will split each other only if they are not equivalent. Protons on the adjacent carbons normally will couple. Protons separated by the 4 or more bonds will not couple. Spin-spin splitting. Often a group of hydrogens will appear as the multiplet rather than a singlet. Multiplets. If the NMR n is equal to nothing but the number of neighboring protons. Number of neighboring protons is equal to 0 plus 1, that shows the singlet. Number of neighboring protons is equal to 1 plus 1, that shows the doublet. Number of neighboring protons is equal to 2 plus 1, that shows the triplet. Number of neighboring protons is equal to 3 plus 1, that shows the quadrat. If number of protons is equal to 4 plus 1, that shows the quintet. Number of neighboring protons 5 plus 1, that gives the sextet. And number of neighboring protons 6 plus 1, that gives the septet. And number of protons rather than 6, that we can measure as a multiplet. It is said to be spin-spin splitting formula. In spin-spin splitting formula, the protons tells about the number of neighboring protons, and number of neighboring protons may be denoted as a capital N plus 1. That is said to be spin-spin splitting. In spin-spin splitting, N is equal to number of neighboring protons that are attached to the observing protons. NMR splitting in simple propane. This is the structure of simple propane: CH3, CH2, CH3. These both CH3 groups are in the same chemical environment because the CH3 group, methyl group, are attached to the methylene CH2 group, and this CH3 group, methyl group, is also attached to the methylene group. So these two protons are in the same chemical environment. So we observe only two sets of protons here. Overall, we have 8 protons. We have 8 protons, but 6 protons are in the same chemical environment, 2 protons are in the different environment. So we get the only 2 types of peaks. Here, first of all, we observe the CH3 group. Number of neighboring protons are only 2 protons. N is equal to 2 plus 1. So it is observed as a triplet. It is observed as a triplet. Here CH2, in CH2 number of neighboring protons, here CH3 group is attached, here also CH3 group attached. Number of neighboring protons, overall 6 protons, 6 plus 1, that is observed as a septet. Here CH3 group is observed as a triplet and CH2 group is observed as a septet in the simple propane NMR spectrum. This is the reference compound, that is the tetramethylsilane. CH2 protons at 1.4 ppm septet and CH3 protons are observed at 0.9 ppm observed as a triplet. NMR spectrum of ethyl bromide. In ethyl bromide, this is the structure of ethyl bromide. We have CH3, CH2, Br. Here 2 sets of protons are present. One is the CH3 group, another one is the CH2 group. CH3 is the methyl group and CH2 is the methylene group. These two sets of protons are in the different chemical environment. A set of protons, CH2 is considered as a set of protons and CH3 is considered as a B set of protons. With the reference of bromine, we have the priority of bromine. So this is said to be A set of protons and this is said to be B set of protons. A set of protons, number of neighboring protons, here 3 protons, 3 plus 1, that is observed as a triplet, and here CH2 is observed as a 3 plus 1, that is observed as a quadrat, and here B sets of protons neighboring 2 protons, 2 plus 1, that is observed as a triplet. A set of protons observed as a quadrat and B set of protons observed as a triplet. In here, A set of protons neighboring only have 3 protons. As per the spin-spin splitting formula, n plus 1, we can apply the n plus 1 formula. N is equal to number of neighboring protons. CH2 protons, number of neighboring protons is equal to 3 plus 1. So it is observed as a quadrat, and CH3 protons, number of neighboring protons, we have only 2 protons. So it is observed as a 2 plus 1, that is the 3 triplet. Next, NMR splitting of the simple acetaldehyde. NMR splitting of the simple acetaldehyde is the CH3 C double bond OH. Here CH3 group is observed as a CH3 group, number of neighboring protons only one proton. So 1 plus n is equal to number of neighboring protons is equal to 1 plus 1, that is observed as a doublet. Here CH group, CH aldehyde group, number of neighboring protons is equal to 3 plus 1, that is observed as a quartet. Quartet at 9.3 ppm and doublet at 2.2 ppm. NMR spectrum of simple toluene. The NMR spectrum of simple toluene includes the A singlet at 2.34 ppm due to the methyl group attached to the aromatic group. We know that the molecular formula of benzene is the C6H6. Okay, here the hydrogen is replaced by the methyl group. So here no hydrogens are present in this carbon. So CH3 number of neighboring protons are 0. So CH3 group is observed as a singlet at 2.34 ppm and these aromatic protons are observed as a multiplet at 7.17 ppm. In benzene nucleus, mostly we observe at 6.5 to 7.5 ppm in NMR scale.